production of chlorine and sodium hydroxide. So these are some of the applications. So we'll try and dive in and look at each one of them and see how this is applicable. So applications of electrolysis. Let's tackle extraction of aluminium. So aluminium is extracted from a bauxite, which is aluminium oxide, using electrolysis. Okay, now this is one of a huge industry where electricity is highly applicable. Okay, very much highly applicable, and a lot of electric current or charge is used to extract aluminium from this ore. So electrolyte, molten aluminium oxide. So the ore, the aluminium ore, the bauxite is heated to a very high temperature to have it in molten state, and then dissolve cryolite. So you get cryolite, you dissolve into this molten aluminium oxide. And the importance of cryolite, it lowers the melting point because you require a lot of energy to have aluminium melted. So to reduce the trouble. In fact, in most cases, these plants where they melt aluminium, they are usually located in high mountainous places for the same purpose that cryolite is playing here, to lower the melting point, because the pressure there is different. Okay? Because apparently, yeah. Also improves conductivity. So you want conductivity also to be improved, and reduces energy costs altogether. So at the cathode, this is what is happening. So cathodic reaction, this cation for the cathode ion, aluminium ion in this particular case, receives 3 electrons for the purpose of producing 1 mole of aluminium. So the ratio of moles, 3 moles of electrons give 1 mole of aluminium. So the molten aluminium forms at the cathode. So these ions will travel to the cathode. They will receive 3 moles of electrons, and this will be deposited in molten form. Of course, later on it will be hardened and to be given different uses regards with aluminium. Then at the anode, because remember the ore is aluminium oxide or bauxite. So what is separating here is aluminium gets a positive charge, oxygen gets a negative charge. So while at the cathode we have aluminium ions gaining 3 electrons, we have at the anode oxygen ions also losing those electrons, becoming oxygen being oxidized to get oxygen gas and give up 4 electrons. So if you were to balance up this these half reactions, if you were to merge to come up with the overall reaction, you need to take note that here you have 4 electrons, there you have 3 electrons. So you know what to do with such numbers. Okay, then you also have oxygen that is produced at the anode. It goes further to react with the electrode, okay, which is made of carbon. So carbon and oxygen react to form carbon dioxide, and this gas is released. So we can also give a few uses of aluminium in the aircraft manufacture, cooking utensils, and electrical cables. So for aircraft manufacturing, is for the purpose of the density. Aluminium has very low density. It's light. Okay, so when you are constructing an aircraft, you don't want something that is heavy, because it might just land in instead of flying over all the way to Malawi to crash right at Mpezeni's palace, and that will be the end because it's too heavy. So you need something that Also, cooking utensils, I think you have a lot of such in our homes, something that cannot be overemphasized. Electrical cables, again, for the same purpose, because of the low density, they are also used as overhead cables. Overhead, that's the key word there. Those grayish cables, the 11 kVs, the 33 kVs, and so on, those that pass through our compounds, those are made of aluminium. Okay, so one of the major applications of electrolysis. B, we have purification of metals. So remember the way I'm using these terms. Here I've said extraction. Here it's purification. Don't confuse the two. You'll be required to use correct terms and you'll be required to be specific to each example. So also electrolysis is used to obtain pure metals. Was the purification of copper. So impure copper is placed at the anode. Then a small pure copper, the cathode, is placed at the cathode. So they're called copper cathodes. Then copper 2 sulfate will be used as an electrolyte, and this is what will be happening at the anode. So at the anode, where you have the impure copper, that mixture of copper with impurities, the copper will begin to escape from the rest of the impurities that will begin to deposit at the base of the cell. Okay, so they will lose electrons at the anode. Electrons will travel through the wires. Then we have at the cathode, this is a reaction that will be taking place now. The pure copper is being formed here, where we have copper gaining electrons and being deposited on the surface of the copper cathode, and the size will begin to increase. So pure copper deposits on the cathode, and we have separated, or actually purified it from the impurities, and from the anode, which are the impurities, to the cathode, which is now pure copper. And in most cases, this is obtained at 99.8% pure. That's how much effective this electrolysis process is. So copper is used in our electrical wires, in our homes, and also electronics. When you open electronics, those of you who are curious, you find that there's a lot of copper wire that is used in the electronics. Also, electroplating. We have electroplating as one of the major uses of electrolysis, or major application of electrolysis. So we have an example that is given here. So electroplating is the coating of one metal with another using electrolysis. So you're going to have the main metal being coated. It's more like it's a form of painting, but this form of painting is more effective, more permanent, and more smooth, and more purposeful. So example, silver-plated cutlery. We've seen quite a lot of these. Last time I mentioned there's no silver plate in here in Lusaka that I've come to see, to be very expensive. Mostly it's just electroplated. Okay, we have chromium plated taps, and also gold plated jewelries or jewelry. So again, gold is not something that you easily found, it's expensive. And what you might have underneath is just a common metal, which is very cheap, but also electroplated with copper for the sake of those that are into jewelry. So the reasons for electroplating mostly is to prevent corrosion. and improve appearance other than increasing the durability of that particular um, metal that you're trying to electroplate. Then also, so here is a typical example of what application of electrolysis might look like, specifically electroplating. So you have, in fact, in this case, the piece of metal that you're using to electroplate would be in pure form. So what is happening is actually the migration of ions from solid, they are dissolved and they migrate to the new cathode. Okay, so an electroplating of spoon is an example that has been given here. So we have a power source, we have the silver metal, and we have the spoon that we want to electroplate. So usually the spoon will be made of, it could be iron or any other, or copper or any other metal, which is slightly cheaper. And which is thoroughly clean, because you don't want to start electroplating when there are still particles, because that would be disastrous. Your electroplating will be not effective. So when a direct current is passed, this is what is happening at the cathode, which is the spoon in this particular case. So it will gain, so the ions, the silver ions will gain electrons here at the cathode and are reduced in this reaction. So this silver solid now settles on the surface of this spoon. So at the end of the day, you might think the whole spoon is made of silver. Okay, so it's deposited on the surface, and what is happening on the other hand at the anode, it's the same silver, and this silver dissolves into the solution to become, or rather, or simply releases electrons, which will pass through this wire and come to the cathode here. So this replenishes the silver ions in the solution or in the electrolyte. So it's a simple process that happens. So you just put the silver, you connect to the spoon, then you have the power source, and then those ions begin to migrate, receive electrons, and settle on the surface of the spoon smoothly, and they are distributed evenly. So also we have electrolysis of chloride solution or brine. So a concentrated sodium chloride solution is known as brine. So the concentrated sodium chloride solution will give chlorine gas as one of the products, also hydrogens, and we have sodium hydroxide solution. So those will be the product. So this one, you need to know how to give the overall chemical reaction. So what is happening at the cathode there? We have water gaining 2 electrons. Now, if you look carefully there, if you split water, water gives you oxygen ion, negatively charged, or -2, and hydrogen ions, +1. So if you just consider one molecule of water, it will give you 2 hydrogen ions plus, okay? And then 1 oxygen ion, 2 minus, okay? So if you look carefully there, you discover that what we are dealing with here is the 2 oxygen or the 2 hydrogen ions, which are plus, they will receive these 2 electrons and they'll form hydrogen molecule. That leaves the ratio of oxygen and hydrogen 1 to 1, and they have a negative charge here. Okay, so hydrogen gas is produced, and this is one of the products that we're interested in. Then at the anode, on the other hand, this is what is happening. We have the chloride ion, which releases 2 electrons to become neutral as chlorine gas. Okay, so chlorine gas is produced here, and it's one of the products that we're interested in here. So we have both hydrogen coming out from the cathode, chlorine gas coming out of the anode, and what is remaining is the sodium ion, and which will react with this hydroxide to form sodium hydroxide solution. So these are the major products that are formed in this electrolysis, or the application of electrolysis in the decomposition of sodium chloride solution. So this is the overall reaction. So of sodium chloride reacting with water as an electrolyte in the electrolysis process will give you sodium hydroxide, hydrogen gas, and chlorine gas. So let's look at the uses of the decomposition of brine or concentrated sodium hydroxide. So chlorine is used for water purification. It's a well-known fact. We also have manufacturing of bleach. A lot of these products, such as jig and other bleaches, they use chlorine. Or even when you just use chlorine itself, you'll be able to achieve the bleaching process. Okay, others have used chlorine or stained clothes, and they have achieved those results because it is indeed used in the process of bleaching. Also, in the production of polyvinyl chloride, PVC, these are basically plastics, so you need chlorine in that industry. So now these uses that I talk about, they are uses at a very large scale. Okay, if you look at purification of water, that's a large scale application or use, because we have almost everyone, even at the water distribution facility, they use these at a large scale. So in talk of production of polyvinyl chloride, we're talking about a huge industry that produces all the plastics that you see around here, and the pipes and everything that are made of the plastics. Then you have sodium hydroxide, which is used in soap manufacturing, paper making, and drain cleaners. So some of the uses: hydrogen, manufacturing of ammonia. So ammonia is NH3. So you can say you need the nitrogen gas and hydrogen gas to come up with ammonia. So huge industrial application there. Sometimes this ammonia can add other things to come up with fertilizers and everything else that we need ammonia for. Ammonia is also used in the laboratory for a lot of purposes in the experiments. Also hydrogenation of vegetable oils. So now this process is also very important. So what you have at the end of the day is oil or vegetable oil, which was purely liquid. It becomes semi-solid. Okay, and when that happens, that can be used in the manufacturing of margarine, butter, or I don't know what other names are there, brands that are there, but it's margarine. So the vegetable oil, when you hydrogenate, You do this in organic chemistry. I think towards the end of your first year, or those of you who continue with chemistry, you go into the details of how to produce margarine. And the process starts with hydrogenation. So when you're hydrogenating, you're basically breaking the double bonds into single bonds by adding hydrogen, and that changes the texture of the cooking oil or the vegetable oil from liquid to semi-solid, just like the texture of margarine itself. And during the Second World War, actually, this is when the process was highly applicable. Because some soldiers somewhere ran out of margarine, and it was very, very cold, especially in the European countries, Germany, and they needed to survive. So to add a bit of fat to their bodies, they were using margarine, adding to their bread and everything else. And when they ran out of that, they were simply hydrogenating the cooking oil and giving them as margarine, and they were applying to their bread, not knowing that what they were eating was just basically cooking oil which has been hydrogenated, and they were very, very, very happy. Thanks to the chemists at that time, they saved the day. And soldiers being soldiers, they didn't know what was happening, but chemists, not being chemists, they knew what was happening. And yeah. So those are some of the major applications. So advantage of electrolysis: extracts reactive metals, purifies metals, separate from the impurities, produces useful chemicals at a large scale, prevents corrosion through electroplating. I don't think if you were asked to state 4 important uses, and I'm using the word important uses, I don't think you can fail to state this. But this is not just for the purpose of exams. I think education should move away from the system of memorizing things. Whenever you hear extraction of reactive metals, these are some of the things that you're going to find in the mines. So you get keen interest and see how you can also add your knowledge and experience to improve this industry here, the extractive industry. Also, purification of metals. What parameters can you adjust to improve the production of or the purification of metal in your industry when you go to apply your chemistry there? Also, production of useful industries. What other resourceful materials can you use to improve that production? Prevention of corrosion. What materials are vulnerable, and how would you want to protect them using electrolysis, electroplating in this particular case? So when you are given such kind of information, your role is not to memorize these things, so you come and give them back to me in the exam. Your role is to get these ideas. You can begin research right now to see how these industries can be improved, how you can apply your chemistry to improve what is happening there. You might think at this stage, obviously they have researched everything, they know everything, there's nothing to add. You find that in the past, people are just memorizing to go and apply this. When you get there, you see gaps, and science is improving every day. So you can also add your weight to scientific discoveries. So in summary, electrolysis is basically the decomposition of ionic compounds using electricity. The amount produced depends on the quantity of electricity passed, and of course, many other factors such as the nature of the electrolyte, the electrons, the potential difference, and many other factors, the concentration, they all come into play. And to basically determine how much of the product is going to be given out. And also how the electrolysis process itself is going to progress. Then Faraday constant is given, also comes into play. It's something that a factor that is used to determine how many moles are going to be produced especially the number of moles of electrons, because in it we have the Coulomb and the mole. So when you multiply the charge or you divide the charge and the Faraday constant, it gives you the number of moles. So it's a factor, it's a constant that is very, very important and widely applicable in our electrolysis journey. So also electrolysis has an important industrial application, including extraction of metals, purification, and electroplating, among production of other useful industrial chemicals. So we can do this one last example. Okay, so here we have, I hope you have calculators there. You have a technician who is electroplating or plating a faucet with 0.86 grams of chromium from an electrolytic bath containing aqueous chromium sulfate. If 12.5 minutes is allowed for the plating, what current is needed? So this example is the same with what we've done, except that this time around it is asking for something different. We are used to a situation where we are always told how many grams are going to be produced, how many grams are going to be, and so on and so forth. Now, the interesting part about this question is that if you are in management or if you are the chemist in charge in the industry and you find that they have produced a certain amount of mass of the metal, or they have used a certain amount of mass of the metal in electroplating, or they have extracted a certain amount. From the amount given, you can tell how much electricity they used using this application. And this is very, very important to know because in most cases in industry, you're going to be dealing with people of different mindsets, okay? But you can make calculations. It's not witchcraft, it's chemistry. And you can catch up with so you might find that probably the mass and the amount of electricity that has been used is not adding up. Then you begin to question how the process proceeded, because you know the conditions, you know the potential differences, you know the metal you are dealing with, the position in each electrochemistry series, you know the amount of time that passed, and so you can calculate, you can get to the bottom of everything and begin to tell them, this is the amount that was supposed to be produced. Can I have the other copper where you are hiding it? Okay, so in this particular case, you have the mass which is produced, and so from this solution, and you spend 12.5 minutes for plating. So what current was used here? Okay, so let's look at the working out. So first things first, chromium is 3+. It gains 3 electrons to give chromium solid. So we know that the ratio of the ratio of moles of electrons to chromium solid is 3:1. Very important here. So moles of chromium deposited. So we know number of moles is mass over molecular mass. This is from the stoichiometry. So this is the mass that was used. That was used in electroplating. So you have the chromium molecular mass gives you this number of moles. So moles of electrons required. Now we have this ratio here. So if the number of moles of chromium is this, then the number of moles of electrons is supposed to be 3 times. So you simply multiply 3 times 0.0165 to get the number of moles of the electrons. So if you have the number of moles of the electrons, then total charge required, you use the Faraday constant here, because number of moles is equal to Q over F. So Q over F. So you can make number of moles the subject, or you can rather you can make Q the subject, because you have the number of moles, you have the Faraday constant which is given. So the charge is equal to number of moles multiplied by the Faraday constant. So I'm sure you've seen how we've done the transition from the number of moles of chromium to the number of moles of electrons. That's why this equation is very important. So then you multiply the number of moles 0.0459 multiplied by the Avogadro constant. So don't mind this value is given. I'm sure you are used to the 96,500, but this is actually the actual. That one is rounded off. But what to use will be given. Don't have to memorize, but at least you need to know the value that is somewhere 96,500. In case there's a mistake, in case I've forgotten the 9 in front, you can't just go on and use the 6,500 or 6,485. You need to have an idea the value. So when you multiply the two, you get the coulombs. This is your charge. Okay. Now we know that charge Q is equal to IT, current times time. So what you're looking for is the current. So you make current subject to the formula, and what you have is Q over T. So we're told that it was 12.5 minutes. So you convert that to seconds by multiplying 60. So this is what you get, and you get to the bottom of the current that was used. Have we lost the screen? Let me just reshare. Is it back now?
Yes.
Oh, all right. That's great. Yeah, so there we have it. We have our current calculated. So you can start. You can be given anything. You can start from anywhere, as long as you know your manipulation, the stoichiometry of your electrolysis. Yeah, you can manipulate anything and come up with anything that you need to know in these calculations. So you can determine the current, you can determine the voltage, you can determine anything. So in the industry, there's no stealing if you're dealing with a chemist. In such cases, they can just see how much Zesco they bought the previous day and how much you have used. Then they'll tell you how much you should have produced. Then whether there are other conditions that led to the low production, then that's what you need to explain and prove. Otherwise, everything is given here, and there's no excuse. So you should have recorded the concentration. You know how to do the concentration, the calculations. You should have recorded everything. And this is where the difference between how much was spent and how much has been realized is obtained. So when you go to industries like Mopani and these other producing companies, the mining companies, they take keen interest in such kind of calculations to see how much is being spent, and but most importantly, the or that you can place in such industry is to see how you can adjust, how you can make the processes smoother or simpler or easier or less costly. Most important, less costly. So improvements need to be made in the industry process, and it all starts with a chemist like you. Any questions? Well, since we don't have questions, everything is clear. We've come to, okay. Yes, go ahead, Bruce.
When you're using electrolysis to extract like metals like aluminum, do we use the same process to purify it, or it is purified right there and then?
Bruce, are you using maybe Bluetooth or something? You're not clear. Try to use the mouthpiece directly so that we can hear you properly.
Okay, so my question is, when we're using electrolysis to like extract aluminum, for instance, do we use the same process to purify it, or it is purified right there and then?
Anybody who got what Bruce is trying to ask? I haven't gotten the question. I just got the first part. Say when you're using electrolysis to extract minerals, but the other part of the question I didn't get. Anybody who got what Bruce was trying to say?
Okay, let me just repeat itself. I'm sure it's clear now.
Now it's very clear.
Okay, so the question is, when we're using electrolysis to like extract metals such as aluminium, do we use the same process to purify it, or it is purified right there and then during the extraction?
All right. That's so. In fact, electrolysis process in most industries, when you're doing extraction, is the last stage. It acts like extraction as well as purification, because the electrolysis process produces a very pure quality product. So you may not need another extra electrolysis to do the purification. Electrolysis is in most cases the last stage. So you find that there is going to be the crushing of stones which contains the ore. There's going to be the concentration depending on the density. So they scoop out the residues, or if your product of interest has a lower density to float. In copper, there's a flotation process. Then there's concentration until they have very good concentration. Then they subject that ore to electrolysis. So for aluminium, electrolysis will act as both extraction and purification, but basically it's extraction, because when you use the word extraction, you are separating a compound, and the compound you're separating is aluminium oxide or bauxite. So the oxygen goes to the anode, the aluminium goes to the cathode, and that's a very pure substance that you're obtaining. So you don't need another electrolysis to purify further. All right. Any other question? Okay, I think we don't have questions. So this marks the end of our topic. We were supposed to meet on Friday, but since we've finished, I will allow, by the powers vested in me, I will allow all the Easterners to go and mourn Mpezeni, So you don't need to have a class on Friday because we've come to the end of the topic. I had to make an adjustment so that we leave Friday free for the sake of mourning the paramount chief. Okay. And if there are any questions, any concerns, you have your class rep, you can forward those concerns through him, then you can have those chats later on. So I think the next topic you're going to have somebody else taking over. From me, for now, it's goodbye, enjoy your day, and God bless. Thank you. Yes, Angela, the notes were shared through the class rep. I'm sure he will share with you guys as I gave him. But if there are a few slides, because I added a few slides, you can still reshare. But those are basically just examples. But all the notes were shared with your class rep. So just ask him, he will share with you. So Kashimba Mwaila, you came late. The class is over. We've just concluded. I'm sure your friends will share what was discussed.